This section have two objectives. First objective, use bisection method. Second objective, use force position method to solve the root. These two methods are numerical method. For our first objective, this method is due to Bolzano. Suppose we wish to locate the root of an equation f(x) equal to 0 in an interval x0 and x1. Let f(x0) and f(x1) are of opposite signs. For example, f(x0) times f(x1) is negative value. Then the graph of the function crosses the x-axis between x0 and x1, which guarantee the existence of at least one root in the interval x0 and x1. The desired root is approximately defined by the midpoint x2 equal to x0 plus x1 divided by 2. If f(x2) equal to 0, then x2 is the desired root of f(x) equal to 0. But if f(x2) not equal to 0, then the root may between x0 and x2 or x2 and x1. Now we define the next approximation by x3 equal to x0 plus x2 divided by 2, where f(x0) multiply f(x2) is negative value. And maybe the root is between x0 and x2. So our x3 will be x1 plus x2 divided by 2, where f(x1) multiplied by f(x2) is negative value. So at each step, either find the desired root to the required accuracy or narrow the range to half the previous interval as figured below. This process of halving the interval is continuous to determine a smaller and smaller interval within which the desired root lies. Continuation of this process eventually give the desired root. Look at the first example. You need to find the roots of this fourth order polynomial function. First step, construct a table. You set a domain from -2 to 3, and we construct a table. After we constructed our table, sketch a graph, and you realize that the first root is between -1 and 0. The value here is -0 point something. And for the second root, the value is between the 2 and 3. So the root here is 2 point something. Based on the graph changes sign between x equal to -1 and x equal to 0. For the first root, it's between the x equal to -1 and x equal to 0. So we have f -1 is positive value. You can check the table. F -1 is positive value. The value is 1, positive 1. And f0 is negative value. The value is -2. So meaning that the sign is from positive value change to negative value for the first root. And for the second root, the graph changes sign between x equal to 2 and x equal to 3. So for the f2, the value is negative value. It's negative 2. And f3 is positive 25. Meaning that the sign change from negative value to positive value. Consider the negative root first. The method we will use is the bisection method, whereby we continually bisect the interval in which we know the root occurs until we obtain the root to the required number of decimal places. For the first root, we know that the root is between x equal to negative 1 and 0. So we let x0 equal to negative 1 and x1 equal to 0. So first, you sketch a number line. We have negative 1 and 0. And from the graph, you know that between the negative 1 and 0, there is a root. And x0, we let the x0 equal to negative 1, so we label the negative 1 as x0 and 0 as x1. And from our table, f negative 1 is positive value. It's positive 1, so it's positive value. And f x1 is negative 2, it's negative value. You can see the sign plus minus, so meaning that the root is between the negative 1 and 0. Okay, so meaning that f x0 multiply f x1 is negative value, because 1 multiplied by negative 2 is negative 2. So we start to approximate our first root. Since we have x0 and x1, so we start from x2. x2 equal to x0 plus x1 divided by 2. So x0 is negative 1 plus 0 divided by 2 is negative 0.5. And we substitute into our function f negative 0.5, or we say f x2 is negative value. The value is negative 1.68. It's negative value. Okay, so now we label negative 0.5. And this is a x2. And we produce negative value. So from this number line, this is very clear. The root is between negative 1 and negative 0.5. It's not between the negative 0.5 and 0. And we repeat the iteration. f x0 multiply f x2 is negative value. And x3 is equal to x0 plus x2. x0 is negative 1. x2 is negative 0.5. Then divided by 2, we have negative 0.75. And this is x3. And you check for the value of this f negative 0.75. The value here is negative value. It's negative value. So, meaning that the root is between negative 1 and negative 0.75. because the sign here is plus and the sign here is negative. Again, we continue to approximate the next root. F x naught multiply f x 3, because plus minus is minus. So the x4 is x naught plus x3 divided by 2. So we have negative 0.87, where here is the value negative 0.87. So this is the x4, and the value here is negative value. And you see the y value, our output is negative 0.07. The value is very small, so we can conclude our first root is negative 0.87. Our root is x value, it's not y value. And when we can start our iteration, normally our output, our y value is modulus f x less than 0.0. Sorry, is 0.1. When your output is less than 0.1, so you can stop the iteration and you can conclude your first root. Second root. For the second root, we know that the root is between 2 and 3. Okay, immediately sketch a number line. 2, 3. We let the x not equal to 2. And x1, 3. And from our table, our output at x equal to 2 is negative value, is negative 2. And the output for x equal to 3 is positive value. So meaning that the root is between the 2 and 3. And fx naught multiply fx1 is negative value. So you can start to approximate the root between the 2 and 3. So we start from x2. So x2 is equal to x naught plus x1 divided by 2. So we have value is 2.5. This is a x2. And you check the output. F 2.5 is 5 point something. It's positive value. So you also know that the root should be between the 2 and 2.5. It's not between the 2.5 and 3. Because you look at the sign, negative and plus. So fx naught multiplied by fx2 is negative value. Because the value here is negative, the value here is positive. So you produce negative value. And the x3 is equal to x naught plus x2 divided by 2. So we have 2.25. Is x3. And you substitute into the function. Check the value. It's positive 0.8477. It's positive value. And the value here is bigger than 0.y. So you have to continue the next iteration to get the smaller value. And the next approximation will be between the x0 and x3. So the x4 is equal to x0 plus x3 divided by 2. And we have the value is 2.13. This is the x4 and the value is negative value. And you substitute into the original function, we found that the value is negative 0.7 and the value is not less than 0.1. So continue to bisect, and the root is between x4 and x3. So x5 is equal to x4 plus x3 divided by 2. And the x4 value is 2.19. It's here. 2.19. So this is a x5. And the value is negative value. 0.0043. So the value is more enough, because the condition modulus of fx less than 0.1, and you can stop at this step, and you can conclude your root between 2 and 3 is 2.19. This is the second method. In this method, choose 2 points xn and xn minus 1 such that fxn and fxn minus 1 are of opposite sign. Intermediate value property suggests that the graph of y equal to fx crosses the x-axis between these 2 points, and therefore a root C x equal to psi lies between these 2 points. So, to find a real root of fx equal to 0, replace the part of the curve between the points A and point B by the code in that interval, and take the point of intersection of this code with the x-axis as a first approximation. This curve. The root of this curve is at here. This is a root. And this is a curve. You look at the curve. This is a curve. Okay, that's our original curve. And first, you can look at this point, this x value, xn. This is a xn and this is a xn minus 1. So the fxn is negative value. Here is negative value. And fxn minus 1 is positive value, because the value here is positive value above the x-axis. Here is negative value. So meaning that the root is between the xn minus 1 and xn. And this method, we form a linear line. So you have, since you let the xn minus 1 and xn be your 2 points, so we can form a straight line. Since we have 2 points, we can form a straight line. The straight line equation based on the first chapter. So this is a straight line, the first straight line. And you see, the first straight line, you let equal to 0. You let the first straight line equal to 0, so you will get root. You will get the root. So we name this root as xn plus 1. And you substitute the x value here into original function. You substitute this x value into original function, you will get this point. It's negative value. It's negative value. So your root is between this point, xn minus 1 and xn plus 1. Because here is plus, here is minus. And you name this point as A1. And you form again a linear line from this point B to A1 point. After you form a linear equation, you let y equal to 0. You will get this root, x value. And you substitute into our original function, the answer is negative value. So you can name this point as A2. And again, you won't get the value, the modulus fx less than 0.1, because still far the distance, you see, still far. So you form again a straight line. You form a straight line. After that, you let y equal to 0 to get the root here. And you perform the iteration until your output less than 0.1, meaning that your root is closer to this root, very close, and you stop. Now, the equation of the joining the points A and B is given by this. And you set y equal to 0 to obtain the root. After you simplify this, you will get this equation. So your x will be your first approximation. And you can change this equation into xn plus 1 according to our figure, our new point. And from figure, fn minus 1 and f xn plus 1 are of opposite sign. So it is possible to apply the above procedure to determine the line through B and A1 and so on. The successive approximations required to obtain the required root. Look at the last example. Solve x cubed minus 9x plus 1 for the root between x equal to 2 and x equal to 3. Meaning that the question just asks you to get one root of this function between x equal to 2 and x equal to 3 only. And based on the given information, we let the x1 equal to 2 and x2 equal to 3. And you substitute the 2 into original function as well as x equal to 3 into the original function. So for the f2 is negative 9 and f3 is positive 1. So f2 multiplied by f3 is negative 9. So we have verified the root is between x equal to 2 and x equal to 3. After we confirm, so we use the formula to approximate the x3. So just substitute the x2, the x1, the fx2, and the fx1 into this equation formula. So we have the value is 2.9, and you substitute this 2.9 into original function to see the output. The output is negative 0.7. So the condition, you see the value is still far from 0.1. So we need to repeat the next iteration. This working exactly same as the previous step, the previous method. So draw a number line from 2 to 3, where the 2 is x1 and the 3 is x2. And for the f2 is negative value, and f3 is positive value. So confirm the root is between 2 and 3. After we perform our formula of the first iteration, the value is 2.9. And we name as x3. The value is negative value. So you know the root is between the x3 and x2. So fx2 multiplied by fx3 is negative value. So x4, use this formula and you calculate, you will get the value is 2.94. And you substitute in our original function, you will have negative 0.02. The value here is x4. The value is negative value. So since the value is more enough, where the condition is modulus of fx, the output is less than 0.1. So you can stop at this step and you can conclude your answer is 2.942. You can conclude this is the answer. Or if you want to get a more accurate root, you can perform the next iteration. Look at the example. If we proceed, perform one more iteration, and based on this graph, this number line, you know the root will be between x4 and x2. So fx2 multiplied by fx4 is negative value, and use the same formula, you will get the value is 2.942. The value here is 2.943. The value here, I round up, I will have 942. And for this one, when I round up, I will have 2.943. And this is x5. And the value here is negative value. And the value is more enough, 0.001. So you look at these two values. Actually, they are no much different. So You either can conclude this is a root or this is a root. They are no much different.